Okay, this is going to be part 3 of the video series on the root test. And if you haven't done it yet, I would definitely watch the first 2 videos. And we'll kind of take a look at a special case that pops up when you're working with the root test. And first of all, I'll assume that you've watched the first couple videos and you know how the rule works and you've already seen some of the example problems. But what we're going to take a look at here is a special case, and it looks like this. When you're working with the root test, fairly often you'll come up with this situation right here. What is the limit of the nth root of n? And this is not as obvious as what you might think it would be. So first of all, I can rewrite this if I wanted to. I can write it as the limit as n approaches infinity. And rather than writing it as the nth root, I'm going to write it as n, and the nth root is like 1 over n. So it actually looks like this. And here's my question. If I go way off to infinity, take the limit of this thing, what's it equal to? Now, you can get a little bit of an example if you have something that looks like this, and it works along this line. Suppose you wanted to find the limit, and suppose I had something like this, 2 to the n power. Now, if I let it be 2, let's make it be 2 to the 1 over n power. So if it's a constant, then if you had a problem that looks like this, it's actually pretty easy. You could use this argument. If you want to find the limit of this thing, as n goes to infinity, the exponent up here, 1 over n, goes to 0. So you'd actually wind up with 2 to the 0 power. Anything to the 0 power is 1, and you'd be good. So looking at this thing, you're saying, well, since I've got a 1 over n, since the exponent's going to 0, you could make the argument that this thing could be equal to 1. But also, look at this problem. Suppose you had a problem that looks like this. Find the limit as n approaches infinity, and suppose it was something like n cubed. Now, in this case, as n goes to infinity, the base goes to infinity, so it's like having infinity cubed, which would be infinity. And looking back at your problem, since you've got an n in the base, you can actually make the argument, maybe the whole thing goes off to infinity. So probably it's going to go off to one of these two, but what you've really got is something that looks like this. So in this problem, as you take the limit as n goes off to infinity, you've got the unusual situation where the base is going to infinity, but the exponent is going to 0, and now it kind of gives you a question. So normally, anything to the 0 power would be 1, as long as it's a constant, but also if the base is getting bigger, then maybe that will offset the exponent. So it almost turns into a race. The question becomes, is the exponent going to 0 going to dominate, or is the base going to infinity going to dominate? And let's look at an informal way of doing this first, and it's fairly easy to do informally. But what I'm going to do is this. Let's start by picking some specific values of n. So what I'm going to do is let's let n be equal to 3. So suppose I had 3, the cube root of 3. So if I let n equal 3, I'd have a 3 here and a 3 here. The cube root of 3, now suppose you stuck that on a calculator. If you did, I came up with 1.44. So what I want to know is, what's happening to this number as I let n go off to infinity? So now just pick a bigger one. Suppose we let n equal 10. Then I would have the 10th root of 10. If you stick that on a calculator, you'll get 1.26. So let it keep getting bigger. This time I'll take the 100th root of 100, so I'll let n get very large. If I do this, this will turn out to be about 1.04. And finally, just to go way out, suppose that this was 1,000. I'll let n go all the way to 1,000. Then I've got the 1,000th root of 1,000, which will turn out to be 1.006. Now, if you keep following this logic, then in that case, then the nth root of n seems to be approaching, if you go down here, notice it's getting closer and closer and closer to 1. So informally, if you just ran some points like this, you can actually show that this limit will not turn out to be infinity, it'll turn out to be 1. So that's an informal way of showing it. Now we're going to do a formal way in just a second, then work a couple problems. But anyways, it turns out, so the nth root of n will turn out to be 1. Now this is important enough. I usually tell my students to do this. Whenever you're working with the root test, it normally consists of these 3 parts, and I like to think of this thing as almost being like a 4th part. So I'm going to come down here and actually write at this point the limit of the, let's put it, n to the 1 over n power as n goes to infinity is equal to 1. And I think that's actually worth remembering as part of the root test. It actually pops up a lot. As a matter of fact, if you see this problem, most cases it's going to show up whenever you're working with the root test. So whenever you have the root test, just remember the limit of n to the 1 over n power is going to be equal to 1. Now that was an informal proof. Let's take a quick look at a formal proof of this, and then we'll work a couple problems. Now, this formal proof is actually kind of tricky, so if you can follow it, great. If not, don't worry about it too much, because to actually use it in the problems is extremely easy. So after we run through this little quick proof here, we'll do a couple problems, and you'll see it's very easy to use. So just follow this again. If not, then you'll still be okay. So what I want to do is this. I want to find the limit of this thing. I think I'll write it over here. So this is going to be the limit of, and again, I'll write it as n to the 1 over n power. And I want to find the limit as n approaches infinity. So it looks like that. Now, the first thing I'm going to do is there's a lot of algebra tricks in this. So what I'll do is make this be y is equal to n to the 1 over n. Now, why do you want to do that? Well, a couple reasons. First of all, I need to get this exponent out of the exponent down to the base, and the only way of doing that is to use natural log. So what that means is I'm going to change this thing over here into this. I'll make it be the limit as n approaches infinity, and I'm going to change this into y. So what you'll have to do now is come over here and you're going to do some work on this side, and then we'll come back to this problem. So starting with this, and this is all just algebra tricks trying to get rid of this exponent. So the best way to get rid of an exponent, of course, is logs. So I'm going to take the natural log of both sides. So the natural log of n to the 1 over n. Now what this allows you to do is by taking the natural log, you can now take this exponent and bring it down in front. And that's what I'll do. So I'll make this be the natural log of y is equal to 1 over n times the natural log of n. I'll put those together, make this be the natural log of y is equal to, and I'll rewrite that as the natural log of n over n. Now what I want is this. I want to know what happens as you go way off to the right. So I'm actually going to take the limit of both of these. So the limit as n approaches infinity of this side, the natural log of y, and whatever you do to one side, do the same thing to the other side. So this becomes the limit as n approaches infinity of this thing. So the natural log of n divided by n. Now, at that point, let's just concentrate on this side. I want to find the limit as I go off to here. Just treat this as a completely separate problem. Now again, if you let n go to infinity, the numerator is going to infinity, the denominator is going to infinity. So this is an infinity divided by infinity indeterminate case. This is going to require L'Hopital's rule. And what L'Hopital's rule says is find the limit as n approaches infinity. If you can't find it for the original problem, take the derivative of the numerator and the derivative of the denominator. Well, the derivative of the numerator is 1 over x. The derivative of the denominator is 1. Now I want to find the limit as n goes to infinity. Well, when you divide by 1, it's as if it's not even there, so we can get rid of that part. It just turns into this right here. And if you find this limit as x goes to infinity, this term right here is going to go to 0. So what that means is this entire thing turns into 0. So this part turned into 0, and we'll just go ahead and bring this part down. So that tells me that the limit as n approaches infinity of the natural log of y is equal to 0. Now we'll sort of separate this off all by itself here. And if you're looking at that, you might think, well, this part right here seems to have absolutely nothing to do with this part over here, but actually it does. So let's go back and we'll finish this up now. So what's going to happen? Now, the next part is based on this, and this is, again, just pure algebra tricks, and that's why this little thing's a little tricky. You might remember one of your rules from algebra was this. if you had something like q, any number can be written as e to the natural log of q. So using this little rule right here, I'm going to rewrite y as the limit as n approaches infinity, and rewrite y in this form right here. So instead of y, I'm going to put e to the natural log of y. So I've got e to the natural log of y. And I want to know what this limit is. Well, now you can do this. Since you know, and again, look at the natural log of y here. You want to know what happens to this thing if you take the limit as n approaches infinity of the natural log of y, what happens to it? Well, you've showed it down here. The limit of the natural log of y is equal to 0. So you can show that this thing right here is equal to 0. So what that does, that gives you the limit as n approaches infinity of e to the 0 power. Well, anything, this is a constant to the 0 power is 1. And if you take, parentheses here, and if you take the limit of a constant as n goes to infinity, that's just equal to 1. So finally, after all that work, you started with this, and you showed that it's equal to this. So you can take this and bring it right back up here, and that shows you that this thing is equal to 1. So it took quite a bit of work to get there, but that is a formal proof of why the limit of this thing right here. So again, informally, you can just show that as n goes off to infinity, this thing seems to be approaching 1, or if you wanted a more formal proof, then you've got that also. Okay, now that part's hard, but watch how easy this makes the whole problem. So the idea is now you know when you start these things, you've got, here's the root test, but just remember anytime you've got the limit of 1 or n to the 1 over n, it'll be equal to 1. Okay, so now with that, let's go ahead and try this problem right here. So what I'm going to do is, again, using the rule, I'm going to find the absolute value, then I'll take the nth root of the function, or the series. So in this case, now, I'm kind of lucky in this case because since n is greater than 1, this thing will always be positive. So in the very first step, the absolute value of the original thing is the original series. So everything's positive. So using the root test, I'll do this. I'll go the limit as n approaches infinity of the nth root of n over 4 to the n. And what that's going to give me is the limit as n approaches infinity. And I'll rewrite it, rather than the nth root, I'm going to write it as this thing to the 1 over n power. So this would be n times 4 to the n, all raised to the 1 over n power. So what that's going to give you, now, we'll now individually raise the numerator and denominator to that power. So this is going to be equal to, first of all, it'll be the numerator raised to that power. Then you've got the denominator raised to that power. So both of them raised to the power. Now, in the denominator, remember, you've got a power raised to a power, so you multiply the exponents. This will turn into the limit as n approaches infinity of, and we'll just leave this one alone right now on the top, 1 over n, but in the bottom, multiply. The two n's cancel out, and it leaves you with 4 to the first power, or 4. So it looks like that. Now, here's where this rule helps out. You've got the, look at the numerator, you've got the limit of 1 over n to the 1 over n, and you know that that's equal to 1. So once you've got this rule down, it's pretty easy to use. If you take the limit as n goes off to infinity, you would have 1 over 4. So 1 over 4, back to your rules again. If the limit is less than 1, then you showed that the series converges absolutely. So since this is less than 1, you can conclude that the original series, so the original series converges absolutely. So it converges absolutely. So that's the first problem. But notice, I'll kind of highlight here, is on some of these problems, you're going to wind up with a limit of 1 over n. And just remember, the limit of 1 over n turns into a 1. And it makes it very easy if you've got that down. And let's do one more example now, kind of the same thing. Now this one, you might recognize, first of all, this would be a p-series. So this thing should converge by a p-series. But let's suppose we decided to try a root test on it. Now again, first step, just like before, is to check and see if the absolute value. So the absolute value of this series, and notice, n is always positive, so the original series will always be positive. So the original series is really the same thing as the absolute value. So now let's try the root test. If I take the limit as n approaches infinity, and I'm going to take the nth root of 1 over n cubed. Okay, what that's going to give me would be 1 over n cubed. First of all, the limit as n approaches infinity. And I'll rewrite this as 1 over n cubed to the 1 over n power. Then I'll make that be the limit as n approaches infinity. Again, raise the numerator to the 1 over n power and the denominator to the 1 over n power. So this would be 1 to the 1 over n power divided by the denominator. Raised to the 1 over n power. Okay, now what that's going to be, this would be the limit of, as n approaches infinity, of, and we'll write it like this, 1 to the 1 over n divided by, and now we'll go ahead and multiply these exponents again. This will turn out to be n to the 3 over n. At this point, you need just a little algebra trick here. The limit as n approaches infinity. Now, looking back at our rule, what we've got is the limit of n to the 1 over n, but you don't have a 3 over n. So you can do this little trick. I'll make that be 1 to the 1 over n divided by, and I'll make this be n to the 1 over n cubed. Because this is the same thing. But the reason I did that, so take this 3 and move it to the outside. And what that does, it gives you a 1 to the 1 over n in here. So now, when you take the limit of both the numerator and the denominator in the top, I'm just looking at this one. As n goes to infinity, this exponent gets, the denominator gets larger and larger. 1 over n, this entire exponent would go to 0. So in the numerator, you're going to have 1 to the 0 power. In the denominator, you know that this part goes to 1, so this thing will just turn into 1 cubed. So with that, anything to the 0 power is 1. 1 cubed is 1. It turns out to be equal to 1. So after all this work, going back to look at the rule, if this limit turns out to be 1, then the root test fails. So in this case, you went through a lot of work to conclude that the root test fails in this case. Try another test, and in this case, a great test, of course, would be the p-series. So if the root test fails, then try another test. But it's just another example to show you where this n to the 1 over n might come from. So anyway, my suggestion is if you're working with a root test, keep these, it consists of 3 parts, but I would almost add this as a 4th part. If you know that the limit of 1 over n is equal to 1, it'll pop up quite a bit in the root test, and knowing this will save you quite a bit of work. So once you know it, notice that the problems themselves are actually fairly easy to work. So anyway, that's a quick look of 3 videos at the root test, and hopefully you're in pretty good shape on those.